Good morning, folks. This is lecture 8 on January 31st, 2023. The agenda for today is starting the subject of first undamped force vibration with harmonic loading, and then look at certain things that arise when we deal with the situation. Now, let me remind you that for the last 3 weeks, we have only dealt with the free vibration. It could have been undamped, where there was no damping present, and there was the damped case where you have damped either viscous damping or Coulomb damping, where the amplitude decreased. Okay, so now we're going to look at the case where a force is also present, and we start with a very common force of harmonic loading, which means a sinusoidal varying load. So let's look at the following situation. Suppose we have a block and sitting on a ground. For now, let me assume that there is no friction, okay, and obviously there is no damping here. So it is being applied a force F of t. The free body diagram is shown here, except that I have not written that there's actually no damping, no friction. So the governing equation is uh, the mother of all equations, except that there is no Cx dot term, there is no damping term, and the right-hand side is not zero. And right-hand side is a very special type, namely it is F0 cosine on omega t. In other words, it's a sinusoidally or harmonically varying load at the driving frequency of omega. Okay? This is very common. For example, if you have machines which are out of balance, they have out of balances, and they all have out of balance. A rotating machine sitting on a table, because of that out of balance, it exerts a sinusoidal or a harmonic loading in the vertical direction. Okay, so now we'll worry about that particular topic later on down the course. Maybe next week we're going to come to that specific application. So some of all the forces basically is mass times acceleration. And if you look at this thing, force F is applied to the right, and spring force is acting to the left. Therefore, mass times acceleration is sum of the forces. One is positive, the other one is negative. Uh, and rearranging it will give you this. Now, notice that if I divide both sides by m, you get k over m, which is omega n squared, the natural frequency squared. This is something that we have done in the past 2-3 weeks, okay? And of course, the right-hand side is going to be f0 divided by m, and therefore we're going to call it little f0. So if you see a little f0, means it's the big f0, the amplitude of the load, divided by m. Now, we want to solve this. And of course, you have done this thing in your differential equations course, but this is how actually it was done. So you guess a solution of the form cosine of omega t. In other words, you're saying that the solution of this type will actually satisfy that equation. That's why we call it a particular solution. And it's just a matter of finding out what big X is, okay? Now, this is not surprising because if you differentiate xp twice, you're going to get cosine back. And if you put cosine over here, you're going to get cosine. So the left side is all cosines, and the right side is cosine, same frequency. And out of that, actually, you can find big X. That's exactly what we're going to do. So we're going to differentiate this thing twice and put it up there and substitute it and clean it up. And you can actually find big X, which is the amplitude of the undamped vibration. Okay. Now, this solution is fine as long as omega and omega n are not the same. In other words, as long as the driving frequency omega of this force on the right hand side is not the same as the natural frequency. If they are the same, you're in trouble. We'll get to that later on. Okay. So the general solution, it is the particular solution that we just got is right here. This term in the front is the big X, okay? And we got this, and the 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 homogeneous solution, in other words, the solution to the case where there is no load, the right hand side is zero. We did it in the last 2, 3 weeks, and it looks like this. In fact, there are two ways of writing this. This is the stuff that we did. This piece is the stuff that we did in the first 2 weeks of the course. There's two ways of writing this. Notice that uh, mm, if you look at this, you can combine a sine and a cosine of the same frequency into a single sine term. For example, there's an amplitude A that depends on the initial conditions, and there is a phase phi, which also depends on the initial condition. And this term is exactly what we call cosine omega t minus tau. Now, in the case where there is no damping, this tau is this tau is actually zero when there is no damping. Actually, you can see right here. In the case of no damping, tau is zero. But if there is a damping, and we'll do that later on, this tau is not zero. Okay, so this is what we call homogeneous solution. It satisfies the mx dot plus kx equal to zero. That's what we mean by homogeneous solution. And this is the particular solution that we guessed, except that I put a tau here, which was totally unnecessary. So again, if you write it like this, combining these two using a trick, okay, basically factoring out square root of a1 squared plus a2 squared, something that we did 2 weeks ago, 3 weeks ago, and you can write it like that, okay? Now, a and phi depends on the initial condition, and this a and this phi depends on the initial condition. And if you wrote it like that, and we have done problems of this type, I didn't write it in that form, I wrote it in this form, a1 and a2 depend on the initial condition. So either this or that, okay? All right, let's move it on, move along. Now, this is a rewrite of what we just did. So if I actually went through the substitution saying that x of 0 is x naught, and if I differentiate what you saw just a minute ago, x prime or x dot of 0 as v naught, and actually solve for a1, this is going to be your a1, and this is going to be your a2. Okay, and of course this last term is the particular solution that we got. All right, let's do an example. Suppose we have a 10 kilogram mass attached to a spring of the stiffness. So we have M and we have K. And it's driven by a harmonic load of twice the natural frequency. So the the driving frequency omega, little omega, you're told that is double the natural frequency that we can find. In just a minute, we'll do that. And the amplitude of it, that means the F naught is 23 Newton. What you want to know is that suppose that the mass starts from equilibrium, and given an initial velocity equilibrium position and initial velocity of 0.2 meters per second. You want to solve it and plot the response. Okay, so let's go. First thing that we do is we find the natural frequency, omega n, which is the square root of k over m, 10 radians per second. We know that the driving frequency, that force on the right-hand side of the block, if you refer to the diagram that I showed you a couple of minutes ago, is 2 omega n. So 2 times 10 is 20. Now, little f naught is big F naught, and big F naught is 23. The amplitude of the forced harmonic, which is big F naught, is 23, divided by m. That's going to give you little f naught, and it's going to be 2.3 Newton per kilogram. Now, this is the coefficient that we need, f0 over omega n squared minus omega squared. So you plug these things in, You work it out, you get this number, and we are told that the initial condition starts from the equilibrium position, that means x naught equal to 0, and given an initial velocity of 0.2 meters per second. So if you go back to the previous slide, where I had this big yellow box there, and plug these things in, you're going to get this thing. That part, that part is, this part is the particular solution. Okay, remember this, the thing that was multiplied by sine was v naught over omega n. Okay, if you go back to the previous slide, I'm not going to go there, but if you go back to the previous slide, plug it in. That's this number, and of course you look at the rest of that expression. Okay, plug it in, cosine of 10t. Now, the particular solution, or what is also called, well, the steady state solution, in this case, of course, doesn't make much sense to refer to it as steady state because this is persisting and that is persisting, but that's okay. So the particular solution with this number being whatever you have here, just plug it in, you get cosine of 20t. This is due to the free vibration. I mean, natural at the natural frequency level, and this is because of the driving load. I really should not say free vibration. This is not a free vibration problem, but if you look at it, this portion of it is imposing the. This portion of it is uh, the free vibration type solution that we got. Okay, let's move on. And if you plot it, of course, you're going to get this. By the way, here I have I've combined the two cosine terms together, but it doesn't matter. It was 0.02 sine 10t plus this thing times cosine of 10t. So I just put all the cosines terms together, all the sine terms together. That's totally unnecessary. Okay, so another problem. We have a force vibration. Obviously, we are doing harmonic loading, okay? It's attached to a mass of stiffness 2000 Newton per meter. So here, this is K. Mass, of course, we don't know. And this, is driven by a harmonic load of amplitude 20 Newton. So this 20 is your F naught, big F naught, and the driving frequency is 10 hertz. What you want to know is the maximum amplitude. Now it says if the maximum amplitude of vibration is measured to be 0.1, that means big. The maximum, if the maximum amplitude is 0.1, this will turn out to be big X. This will turn out to be big X. You'll see why in a second. Uh, we want to find the if the maximum amplitude is 0.1, 0.1 meter, and assuming that it starts from initial rest condition, okay, no velocity, no deviation from the equilibrium position. What you want to do is find the value of mass. Okay, so remember this is your this is your big X, and what big X to be 0.1. Okay, okay, and because of this condition, you can see that because of this, if you plug these two pieces of information into that formula that I had 2 slides ago, the big yellow box, you're going to get that expression. Okay, that expression. And if you clean this up, by cleaning up, I mean that you have the difference of two cosines. If you go from your trigonometry, how to do the cosine of alpha minus cosine of beta, that's what I mean by cleaning up. So you put these two together, okay, and you get this. Actually, I may have to. I will rephrase what I said. This is not quite big X, because if you go back, let's go back here. Sorry, we're going to go back there. Uh, the thing for big X is this. is this. It's just that when V naught is 0, X naught is 0, and you put these two together, is that you're going to get, yeah, you're going to get a 2 there, okay? So now, uh, here's the solution. Here's the general solution, uh, total solution, okay? Uh, and if you have the difference of two cosines, you can write it using trig identity, cosine of alpha minus cosine of beta. You can take these two terms and add them up, divided by 2, and you can take the difference of them and subtract them, obviously, and divided by 2, both of them are sine. The difference of two cosine can be written as the product of sine and sine. So we get this. Now, this is the maximum amplitude of the present problem. Okay, this is not big X. Actually, big X, as I told you, was actually uh, F naught over this, but don't worry about it. For this particular problem, when you combine these two, this is the maximum amplitude. The biggest amplitude for the solution is this, because these cannot be bigger than 1. The biggest that both of these can be are less than 1, or the biggest that they can be is 1, but this is the maximum. And this number is 0.1, we're told. However, let me remind you that little f naught was big F naught over m. Now we have some of the numbers here. This is the K stiffness is 2000. F naught, you're told, is 20 Newton, right up there. We are told that the driving frequency is uh, 20 hertz, okay? And this is a mistake. This should be 2 times 10. I don't know, why do I have a 2 here? Just 1 second. That is a mistake. That should be 10. This is a mistake. That should be 10. Okay. 10 hertz is 10 times 2 pi. Okay. I'll fix this thing in the lecture. And you plug it in, you calculate M. Just make sure that this is corrected. Okay. So it's going to be 0.405 kilograms. Solve this thing for M, you're going to get 0.405 kilogram. Now, what if these two frequencies, right now we said one is 2 hertz, one is 2 hertz, okay? One is 2 hertz, 10 hertz, 10 hertz. And the natural frequency, we can actually calculate it, okay? We can calculate natural frequency, which is K over M. Once you find the M, you can plug it in here, and you have a K, and you have a natural frequency. This is natural frequency squared. But let's go to the next line. What if these two are actually close to each other? Okay. So I'm rewriting that same expression that we saw a minute ago. Okay. So starting from initial condition, this is the general solution. Part of it comes from the guessing solution, which is this at the driving frequency. Part of it comes from that homogeneous solution. That's why it has omega n. And using trigonometry, trig identity, we just write this thing as sine times sine, but one is the difference of the two frequencies, the other one is the sum of two frequencies, divided by 2. Now, notice that if omega and omega are very close to each other, this difference is small. So this is a small number, as opposed to omega plus omega n. Okay, so this is small, but in comparison to that guy, so we can view this thing as being large and this thing as being small. So we have something that is varying very fast as opposed to something that is varying relatively slowly. Okay, so uh, I just rewrote this thing down here, right? See, this thing is written there once again. It's the same thing rewritten here. Notice that this is a very small frequency. It has a very large period. So this one is it is a small frequency. That means large period, okay? And this is a very large number compared to this. and therefore small period, small period. Large frequency, small period. So if you actually plot this kind of a solution, you're going to get a slowly varying amplitude. This slowly varying amplitude comes from this term. This term will give you that dotted curve, and this term is going to give you the rapidly oscillating portion of the problem. This phenomena is called beat. Rapid oscillation with a slowly varying amplitude is called a beat, or a beat phenomenon is taking place, and the frequency of the beat is actually this. Okay. Yeah. Let me give you an example here. So this is sine omega nt. I plotted two curves here. Sine omega nt, where omega n is 4.4 hertz times 2 pi radians per second, 4.4 hertz. And I have another sine curve with a different frequency, but very close to it. So this is 4.4. This is 4. 4 hertz, 4 hertz, 4.4 hertz. So they're close. They're close. So if you plotted what I just showed you, the sine of this difference of frequencies over 2 times t times sine of the sum of the frequency over 2, you're going to get this. And notice that you can work it out. If you look at the omega beat is the difference of these two, okay, which is the difference of uh, in radians per second. If you work this out, this number and that number, work it out and get it in the form of radians per second. Don't take the difference of 4.4 because these are hertz, okay? So multiply them by 2 pi, subtract them from each other, and so if you take 2 pi over this, you're going to get the frequency or the period of the large oscillation, which is 2.5 seconds. You can see that. Good. Now, this discussion assumed that actually these frequencies were close to each other. In other words, the driving frequency and the natural frequency were close to each other. What if they are the same? What if they are the same? Well, let's go back to the solution here. This was my equation, and we are assuming that this omega is the same as natural frequency of the problem, which is square root of k over m. Let me remind you that we divided by m for convenience. This step is not necessary, but I wrote it like that. Divided by m, so k over m is omega n squared, and big F naught over m is what we call little f naught. Now, that solution that we guessed is no good anymore. Remember, we made a particular solution. We guessed a particular solution of the form big X cosine of omega t. And then we went and plugged in cosine of omega t in here and differentiated twice, plugged it in there, and solved for bx. You can't do that anymore. You can try it. That's no good. However, this one will work. Remember, these things were covered in your second year differential equations course. Okay, so I'm just reviewing these, and we use it. So we take that guy. This guy will work. We take this guy and plug it in there, either in this or the top one, and clean up. So uh, uh, what I have done here is if you take this, okay, t times sine of omega t, right here, t times sine of omega t, and this is just our f naught over m, no problem. If you take this, okay, if you take this and you plug it in there, okay, you can actually solve for big X, and big X will come out to be uh, f will come out to be f naught over 2 omega. So this think about it as your, I don't want to call this thing big X anymore, but if you take that and stick it in there, you can actually, okay, get the value of X, big X, which apparently is F naught over 2 omega. All right, so here's the situation. If you have any initial conditions, in other words, at t equal to 0, x equal to x naught, and v equal to v naught, so you take the, go back here, take this, apply your initial conditions, you're going to get v naught over omega and x naught. Okay, you can try this. When t is 0, this goes away, this goes away, you say x of 0 is x naught. You differentiate this thing and then set t equal to 0, you will see that you're going to get x dot at 0 equal to v naught. Okay, you will see that. And you'll notice that there is no distinction between omega n, because they kind of disappeared. Omega n kind of disappeared because, look, omega is omega n. This is the initial velocity, initial position, and this is the driving frequency. And as I said, needless to say, omega n is the same as the driving frequency. And if you plotted this, you get something like that. In other words, the amplitude of the oscillation, actually grows bigger and bigger and bigger. And this is what we call resonance. Bad idea. You cannot have resonance, because what happens, you can see that as time goes on, the amplitude becomes unbounded, and in fact, it goes to infinity. I mean, physically, this can't happen because there's always damping, and that damping will dramatically change the problem, as you will see. So the amplitude of vibration becomes unstable, becomes unbounded at omega to omega n, and this causes failure. Because when we have large amplitude, we have large stresses in your component, and that can lead to disaster. Okay, let's do some problems here. So we have a simply supported beam like that, 4 meters long, and on it we have a motor, which could have some unbalance, whatever. Motors always have unbalance. And this motor, once it turns, it puts a harmonic load, sinusoidally varying harmonic load on it. Don't let it confuse you that this is cosine and I'm talking about sinusoidally. That sine and cosine essentially are the same thing, but probably I should say harmonically loaded. We have the dimensions of this bar. And the question is, what is the RPM of the motor, which leads to disaster, severe vibration? So first of all, we are assuming that this is made out of steel, and the density of the steel and Young's modulus are given here. Now notice that this problem can be viewed as a fancy spring and a mass. The mass is the mass of for example, the beam. You can take the mass of the beam, work it out. So first of all, the stiffness, simply supported beam loaded in the middle, has a stiffness of 48 EI over L cubed. We've done things like this. Now the mass of the beam is the density of the steel times the length of it times V and H. And if you this is 56 kilogram, roughly 56 kilogram, based on the information that's given to you right there. Now, you need the I, because to find the stiffness, you need I, 1 over 12 BH cubed. I think this was, B is 0.3 and H is 0.6. You plug it in, you're going to get this number. So the stiffness is, based on the formula here for simply supported beam loaded right in the middle, is that number. Okay, now, what's the natural frequency? K over M. You put the stiffness that we just calculated divided by mass is this. So if the speed of the motor is translating to 38 radians per second, you're in trouble. And if in fact you convert this thing to RPM by dividing it by 2 pi and multiply it by second, because we're talking about minute, if you divide it by 2 pi, you're going to get it in hertz. And if you multiply it by 60, you're going to get in round cycles per minute. Okay, 366. So if the speed of the motor reaches 366 RPM, trouble. So now, this is the big picture of what follows. Right now, So right now we have no damping. This is kind of a review. Maybe I should have said what followed, okay, instead of what follows, because we have already done that. So right there, initial condition, mother of all equation, the right-hand side is not zero. It is equal to f of t, and f of t is harmonic. The general solution has two parts: a homogeneous solution when you set this thing equal to zero, and a particular solution, that guessing solution, basically. So when we have a damper here, you'll see that, oh, actually, I just realized that I have a damper here. So I should have put a damper there. I'm really sorry. This diagram, I should have put a damper here. And the mother of all equation, which has damping in it, is right there. So this is not what we did. This is actually what follows that we will do. So the only thing is that there's a damper missing there. Okay. So the solution, homogeneous solution, is what we call transient. We already know that. If you set this thing equal to zero, you know everything about solution of this thing equal to zero. And the particular solution, okay, the particular solution, which is called the steady state solution, okay? We'll see. Now, this particular solution is no longer what we had before, because that was based on the fact that there was no Cx dot here. It came out to be that very simple expression. Now, this transient solution, we have learned about it in the first 2 weeks of the class, can be written like that, or it can be written as C1 e to the minus sine omega dt plus C2 e to the minus sine omega nt cosine omega dt. Okay, we can write it like that. So the two sine and cosine are combined into simple amplitude and phase. And this one is what we're going to be doing today. Okay. Now remember, as time goes on, this guy, because of that negative sign, gets smaller and smaller and smaller. It will eventually die down. And this is what we're going to learn today is going to persist. That's why this is called steady state solution. So in the case where there was no damping, we did earlier today, uh, I didn't want to call it steady state, but it was that particular solution really. But maybe the choice of steady state would not have been good, and that's why I didn't do that. Okay. All right. So this is the correct diagram. I forgot the damper. All right. So once again, here's the mother of all equation for that setup. If you divide this thing by m, obviously you're going to get omega n squared here because you have k over m, and then you have c over m, and you can show that we already talked about this thing in the second lecture. This c over m can be written like that. Now the good thing is that when you write it like that, there is not three components, three elements, m, c, and k. They reduce to damping ratio and natural frequency. Okay. So the advantage of dividing this thing and writing in standard form, it's called standard form, is that the only thing in it that's important is omega n and xi. Here, there's m and c and k. It's not quite clear how they relate to each other. Now, this f naught came from the fact that little f naught came from the fact that I divided both sides by little m, which we decided to call f naught. Okay. Everything else we know, these are the stuff that we have done. The solution, instead of before being big X cosine of omega t, now it is big X cosine of omega t minus theta. Okay, and that happens because there is a Cx dot term. Okay, because when you differentiate cosine, you get sine. It was not as easy as if this thing was not there. We didn't have to worry about this when we did undamped solution, because I told you that although I wrote it, but theta comes out to be zero. It's not necessary. But here, we have to carry it. This is the guessing solution. We have to find out what big X is and what theta are. What theta is. Okay, now remember, this thing, if you want, you can write it as instead of amplitude and phase, you can expand cosine and write it in this form. That's entirely up to you. But in this particular problem, to get to our solution, to get to our big X and theta, it is better if we handle it like this, okay? So we're going to write it like this. Once we find AS and BS in terms of what we know, then we can find theta and big X. Okay, so the guessing solution, I already wrote it there. It had an X in it, big X, the amplitude, and theta. Okay, so you differentiate that once, you differentiate that twice, plug it in, and clean it up. Now notice that on the right-hand side, your little f naught cosine of omega t turned into 0 because I brought that to the left-hand side. See that? F naught, little f naught cosine of omega t. Where did that come from? It was actually on the right-hand side. We just move it to the left. Why we wrote it like that? We have something times cosine of omega t plus something times sine of omega t equal to 0 for all time. The only way that can happen if this is for all time is that if these two parentheses are 0, and if you make this thing equal to 0, you get that. If you make this thing equal to 0, you get this. Solve for AS and BS. Being in your fourth year or third year, you know how to solve two equations and two unknowns? Right there. So just look. On the right-hand side, we know omega n because it's the natural frequency of our system. We know the driving frequency, omega. Damping ratio, we know it. And little f naught is the big F naught, the amplitude of the applied harmonic load divided by little m. We know AS and BS. And if you go back to the previous slide, write it, and then use this trick of when you have a sine and cosine of the same frequency, how do you combine it into a single cosine term? Okay, remember, let me go back here. Let me go back. Remember, we want to write it like that. But we decided to take the high road. We wrote it in this form, AS cosine of omega t plus BS sine of omega t. These are the same frequency. That's what makes it work. You can combine these two. The expression for AS and BS, we got, it was horrible, but we got it. You can combine these two by that trick of taking the square root of AS squared plus BS squared out, and there's going to be some stuff left here. Then one of them is going to be sine of theta, the other one is going to be cosine of theta, and there we are. This is what you get. Okay, this is after the two sine and cosine with AS and BS in front of it, with these horrible AS and BS, are going to get combined into a single cosine term with an amplitude. This is the amplitude, and a phase, and this is your theta. Okay, so this is we already saw, and we move on. Let's do a problem. So suppose we have a one-story building, okay, and the columns will act as the spring. You apply a load here, it will deflect to the right. We are assuming this is a rigid floor, a mass of m, and there is a damping because of either individual damper that we installed or because of damping in the joints, etc. So this is represented by a mass spring damper system, and there is a harmonic load acting on it in this direction, which we put here. We know everything about the solution of this problem. It was the last 10 minutes. Okay, we got it. Now, what do we have here? We have the mass, 100 kilogram. We have the stiffness. Harmonic force 500, that's a big F, that's 500 Newton. And the frequency of driving load, this is this omega, is 15. This is 15. And we are also told what the damping ratio is. So there's a few things that we have to do. Basically, we want to plot this thing. We want to plot the response x. We want to get it and plot it. But let's see now. First of all, it says for the sustained or steady state vibration, determine the type of determine ah, what it really should say, and I'm going to clean this up when I talk about it in class tomorrow morning, is that determine, forget about this. Oh, this used to be the insert formula from Microsoft equation editors type equation here. Forget it. So here, for the sustained or steady state vibration, determine the amplitude of the steady state displacement. This means the big X, okay? The phase with respect to exciting force, this is theta, maximum velocity of the response, okay? And for the initial condition given here, because notice that these things do not require the initial condition. These things pertain to steady state vibration, okay? But if you want to plot the whole thing, we have to know the initial condition, the entire solution, including the transient that dies out, okay? Um, yeah, determine the structure that describe the total displacement of the structure as a function of, this should be time, function of time. I think I've cleaned this up. I put this, copied and pasted this figure. That's why it covered it. It should be function of time here, okay? So there's got to be a cleanup here that I have to do for tomorrow's lecture. Okay, smooth. Okay, these are given. Out of these two, out of this stuff, first of all, out of M and K, we can find natural frequency. We can find the damped natural frequency. Little f naught is big F naught over M, 500 over 100, 5. Big X, just plug it in. You know omega, you know omega n, you know xi right there. Just literally plug it in. You see, this is a little f on the top, little f naught on the top, which is 5, divided by square root of omega squared minus omega n squared, quantity squared, plus 2 xi omega, omega n, and that's the number. And theta is that phase angle that is asked us to find. Is just look at the formula, it's tan inverse of 2 xi omega, omega n, divided by omega squared minus omega n squared. And work it out, it's 0.33 radian. You will see later on, I will, this business of omega squared minus omega n squared is not that clean. We're gonna rewrite the expression for x in terms of something called frequency ratio, omega over omega. And right now, just literally plug it in. But I'm going to show you later on that it's better to write this thing in a different way. Anyway, all the stuff goes into this because this is the steady state solution. We just calculated big X. We just calculated theta. Just plug it in. This omega is the driving frequency, which happened to be 15 radians per second. Okay. So let me remind you, we now have to find the constants for initial condition. So remember the two ways of doing it. One is to say C1 times e to the minus psi omega n t cosine of omega dt plus C2, same exponential, sine of omega dt, plus the thing that we just got. The thing that we just got in the previous transparency was this big X times cosine of 15t minus 0.33. This is what we got in the previous slide. We have to find C1 and C2. And you have to do it when you write the entire solution. Okay? This is the transient, which will die down. This is the particular solution, which will never go away. And C1 and C2, you get it by initial condition. X naught is 0.06. and V naught equal to 0. So this one-story building, uh, we gave it an initial condition. We gave it an initial displacement of 0.06, I think this is a meter, so that's 6 centimeter, and then let it go. Okay? Let it go, of course, not quite let it go. What I mean is that initially that's the condition, and then this motor or this harmonic load is acting on it. This let it go means a free vibration. So you move it to that position and let the harmonic load acting on it. Okay. Okay. So if you do that, you're gonna get the value of C1 and C2. Just literally plug it in right there. We find this is C1, this is C2. If you look at the transient part, notice that this is dies out. This is the first part of it. This is the steady state. It never go away. This is the big X cosine of omega t minus theta. I think on some occasion I called it tau theta. That's what I meant. If I say tau, I meant theta. But the response of the system, the total response is the sum of these two. And notice that when you add these up and plot it, you get this. Look, if you're in the building business or you're in design business, this thing you know that it's going to go away. So most of the design, in many cases, is interested in the steady state response, not in the transient part that dies down. Now, before I stop this thing, I want to show you something that is, uh, you see it in every vibrations book, including the one our own, but I, uh, uh, I want to caution you, this gives you understanding, better understanding of what is going on. But generally speaking, will not allow you to solve problems. Okay, but it's a good idea to know this. So in a situation, this is called a vector representation of a single degree of freedom system. Okay, vector representation or phasor diagram. Vector representation single degree of freedom vibratory system under harmonic loading. It's very important. Loading harmonic, single degree of freedom, vector representation, and they called also phasor diagram, or some version of it is called phasor diagram. And you might have seen this thing in your first circuits course, or something called phasor diagram and things like that. Now, this diagram does not apply to non-harmonic load. But here, if it's harmonic, then whatever I show you makes sense. Let's go through it in detail. First of all, here's what happened. The, the steady state solution, big X cosine of omega t minus theta. And once again, I apologize if I call this thing tau at some point. Now, you take the derivative of this, and you're going to get x dot equal derivative of cosine is negative sine. But sine of omega t minus theta, you can also write it like that. Okay? Sine of omega t minus theta, you can add a 90-degree to it and convert the sine to cosine. Basic trick. And if you differentiate this thing one more time, you're going to get I found a mistake here. Why don't we fix this thing right now? I found a mistake here. There is a minus sign there. Minus sign there. Let's get it up. Okay, good. So I want to show this thing as a vector. First of all, f naught, f of t equal to f naught cosine of omega. So I'm going to draw this. Let me see for a second. Just remember these things. We're going to go to the next slide because I'm going to show it to you one by one. Okay, this is fine, but I want to show it to you in a more systematic way. This is our guessing solution. This is the velocity, and there's the acceleration. We go to the next slide. Okay, there is the guessing solution. This is the mother of all equations. So F naught, just look at F naught. It can be viewed as a vector, and the vector that is turning at velocity omega t. If you look at the projection of this vector on the horizontal axis, you're going to get F naught cosine of omega t. That distance is F naught cosine of omega t. That's obvious. Hypotenuse times cosine is going to give you the side, which is the right-hand side of this equation. Now, x, solution is like that. Solution is like this, x of t, as a function of time. So if I take big X right there, big X, the amplitude, and draw it here as a vector, notice that this angle between F naught and F naught and this blue vector is theta. Just literally look, omega t minus theta. Okay, so that's this angle. See that? This angle is omega t minus theta. And if you look at the projection of that on the horizontal axis, you're going to get big X times cosine of the angle that you see here, the angle between the green line and the X axis, horizontal axis. And that angle is omega t minus theta. So cosine is going to give you that, which corresponds to this. Okay, kx, k little x is going to be k big X cosine omega t minus theta. Okay, good. Move on. This was big X. If you multiply it by K, you're going to get the blue dotted line, which is K big X. So that actually is right here. Okay. What you see, the green one is big X times the cosine of that angle. The blue one is K times big X times the cosine of this angle, which is right there. Now, this is the damping force. Think about it as damping force. And we know that damping force has to do with velocity, right? Cx dot, c little x dot, c time velocity of the damper. Think about it like that, okay? And way at the beginning of the term, maybe the second lecture, I told you that this damping is the velocity is actually leading the displacement. Velocity leading the displacement by 90 degrees. Okay, so if you look at this and you look at this projection on the horizontal axis, it's going to be c omega x times the sine of that angle. That angle is the same as this angle, which is omega t minus theta. So you can see that cx dot, the damping term, vectorially can be represented by this red dash, the vector, and that horizontal component of it is going to be exactly what this thing is. Finally, if you look at this is your inertia vector, so mass times acceleration. Now notice that I did not put a minus sign there because this direction is already reversed. You can see that this direction is already reversed. And it's right there. This is the minus sign that I forgot. And yep, so that, if you look at its horizontal component, is just times the cosine of omega t minus theta. So this equation can also be vectorially viewed in this way, and this entire structure, this entire thing is rotating about the origin at angular velocity of omega t. That's what the phasor diagram is. Now, look at a few special cases. First of all, if damping is small, Just look at that diagram that I drew for you a minute ago. If damping is small, this thing is small. This red arrow is small, which shows you that this angle theta, this was the angle theta between the force and the purple arrow, which was the force, and the green arrow, which was the amplitude of displacement. If this is small, theta is small. You know that. Very small damping give you very small phase difference. Now, and very small energy dissipated by the damper. Very small damping, very little energy dissipated. Now, basically, the energy mostly goes into some of it is going to be dissipated because if there is some damping, obviously this is not going to be zero. So most of the energy goes into kinetic energy, which is basically from the inertia, and the spring stored energy stored in the spring, which is right there, potential energy. Now, if there is no damping at all, if there is no damping at all, then this red arrow does not even exist. So actually, this is a situation. The the input energy due to this external force only goes into stretching the spring and kinetic energy. And basically, the diagram looks like that. No red portion. So this corresponds to an undamped force vibration. Okay. This whole thing turns about that point by omega t, right? Let me go back here. By velocity omega, which means turning that angle. It's going to be turning, but it's going to be omega t. Now, one thing I want to tell you is that phase difference is zero. If there is no damping, this red one is zero. Theta is zero. This is why when we started the lecture today, first I considered the case that there was no damping, okay, and found the force vibration of undamped system, and there was no theta there. In fact, I wrote a theta, but I said that that theta is zero because it's an undamped problem. At resonance, this angle theta is 90 degrees. I mean, just look at the formula for angle theta. You see that theta, tangent of theta is going to be infinity. You just look at it, you're going to have tan inverse of infinity. Okay, in the formula uh, for uh, for damping, for tan inverse, the expression at the bottom is going to become zero, so that's going to be theta equal to 90 degrees. All the external energy provided by f of t, that harmonically load, is going to go into damping. All of it. This and this are the same length, okay? And the kinetic energy, inertial force, inertial force is balanced by the spring force, okay? Uh, yeah, obviously that's what this 90-degree means. F of t and x of t is the phase difference between the displacement and force is 90 degrees. Inertial force is completely balanced by the spring force. All the external energy provided by this machine that's vibrating is going to go into damping at resonance. Okay, so that brings us to the end of the lecture. It took me 1 hour here. Probably in the class it'll take me an hour and 10 minutes because there's some question asked, etc. Usually these lectures about usually the tape lectures are about 10 minutes shorter than 10, 15 minutes shorter than what happens in class. Please make sure you are on top of things. Do not let these things pile up. Okay, I told you that this is not a course in math, but there is no way you can get away with the fundamentals, basics of mathematics, which is in your case, in this particular application, vibration is differential equations and a little bit of linear algebra later on. Not now. there's no way you can get away from it. Okay, so it's not we put it this way, a fluffy course. Good luck, and see you on Thursday. I'm going to clean up my lecture now, all the mistakes that I made in the lectures.